functions and their graphs. Okay, so 3 squared is 9. So here's my base. My exponent. And then my result. Since 3 squared is 9, I can write that as log base 3, here's the base, of the result, 9, is equal to the exponent, 2. So logarithms are just exponents. So the properties that we will give for logarithms are just the properties of exponents. So the logarithmic function, let me assume here that the base b is greater than 0, so that I'm not dealing with complex numbers. And the base is, well, if the base were less than 0, I'd have complex numbers. And if the base were 0, then I would not have an injective function. And similarly, if the base is equal to 1, I would not have a injective function. So assume the base is greater than 0 and not equal to 1. Then the function f of x equaling log base b of x is the inverse function of the exponential function g of x equaling b to the x. So with the above assumption on the base, that the base is greater than 0 and not equal to 1, the exponential function will be real valued and injective. So we can determine a inverse for that exponential function, and we call it the logarithmic function. Notation, common logarithm. When Napier first invented logarithms, he did this for calculations involving numbers of base 10. And so if you just see on your calculator log and there's no base, then this will be called the common logarithm, and we will assume that the base is 10. And so if you see the notation log x, it just means log base 10 of x. It is the common logarithm. The natural logarithm. The natural logarithm is denoted by lnx, and it is just the log base e of x, where e is Euler's constant. Let me recall again what Euler's constant is. So e is just the limit as n gets large, as n goes infinity, of 1 plus 1 over n to the power n. It is the limit as x goes to 0 of 1 plus x to the 1 over x. It is the sum of x to the n over n factorial for n equaling 0 to infinity. Let me just sort of write it out. It is 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the 4, etc. E is just the sum, n equaling 0 to infinity, of 1 over n. It is just 1 plus, well, 1 over, maybe I'll run, plus 1 over 2 plus 1 over, and maybe I'll write it this way, 2 times 3 plus 1 over 2 times 3 times 4 plus etc. Instead of writing out the factorials, I'll obviously this was the 24, this was the 6, etc. Okay, so that is E. Or another way of thinking about it, E is that base of the exponential function such that the slope of the tangent line is the line that best approximates the curve at a point, in this case, it'll be the origin. Base of the exponential function such that the slope of the tangent line to the curve y equaling e to the x has slope 1 at 0. If I graph the log of x, suppose b here is greater than 0, then it is always increasing, concave down. It has a vertical asymptote at x equals 0. It has an x-intercept. It has no horizontal asymptote, and it has x-intercept at 1. Okay. And that's what the graph of the logarithmic function looks like for b greater than 1. For b between 0 and 1, it looks like this. It is always decreasing, concave up. It has a vertical asymptote at x equals 0. It has no horizontal asymptote. It has no y-intercept. And it has an x-intercept at 1. So let's do some examples on page 448. Problem number 22. Write each equation in logarithmic form. So I've written this in exponential form. 1/3 to the power -3 is 27. Let's rewrite this as a logarithm. So I have log, base, well, the base is 1/3 of -3, so that's the exponent. Remember, logarithms are always exponents. Is equal to the result, 27. And so I can rewrite this exponential form in logarithmic form. Let me do problem number 32. Write each equation in exponential form. And so let's rewrite this in exponential form. The base is 7. The exponent, remember logarithms are always exponents, is -2. And there is equal to the result. And the result is 1/49. And that is your answer. And so I've written this logarithmic expression as a exponential expression. So I've written this, I've written this first logarithmic form in exponential form. Let me do problem number 48. Find the value of x. Okay, so let's find the value here of x. Okay, so to find the value of x, well, since this started out in logarithmic form, let's write this in exponential form. So the base is 4, the exponent is 1/2, and the result is x. And so an exponent of 1/2 is the same as the square root. The square root of 4 is 2. And so x is equal to 2. Let me do problem number 86. Use a calculator to find y to 4 decimal places if possible. Okay. So ln y equals 2.6490. So let me rewrite this in exponential form. So the base is e. The exponent is 2.6490, and the result is y. And so let's just plug this in. So plugging into my calculator, I get 14.13989,168. And so to 4 decimal places, I get that y is 14.13, okay, 14.1399. And that is your approximate answer. Okay, let's do problem 113. Graph each function. So let me write this as y equals log base 3 of x plus 2. So in this case, this is just a translation of y equaling log base 3 of x. I'm replacing x by x by 2 units to the left. Okay, so let's draw this. Oh, actually, notice the following. So even though I'm doing this, I'll do both of these. So vertical asymptote. To find a vertical asymptote for a logarithmic function, you just set what's inside of the logarithm equal to 0. And so in this case, the vertical asymptote has the equation x equal -2. Notice that there is no horizontal asymptote because it's a logarithmic function. Let's find the x-intercept. To find the x-intercept for a logarithmic function, you just set what's ever inside the logarithm to 1. So in this case, x is equal to -1. So my x-intercept is at -1, 0. Okay. So now let's sketch the graph of this. Okay. Oh, and y-intercept. Actually, since I have room, let me do the y-intercept. It's not really going to give you anything nice, but I have room, so I might as well. So in general, I don't usually find the y-intercept, just because it's usually just nothing nice. So this is equal to log base 3. To find the y-intercept, you replace x by 0. And so this is just log base 3 of 2. And who knows what that is. So the y-intercept is at 0, comma, log base 3 of 2. So now let's sketch the graph. So first, let's sketch the graph of y equaling log base 3 of x. So the graph of will look something like this. That's not bad. It actually intersects at 1. So this is a graph of y equaling log base 3 of x. It's actually, if you turn this, if you rotated this graph by 90 degrees and then flipped it over, about the new x-axis was pointing upward, the graph of y equaling 3 to the x. And so this is what the graph of y equaling log base 3 of x looks like. Okay, so now, let's translate this 2 units to the left in the negative x direction. Question? So 2 units to the left. So if I do that, notice that this y-axis will actually move 2 units over, and I'll actually sketch it. So the axis now is x equaling -2. And the graph, so this goes 2 units over, so that means that this goes to -1, if I can actually draw it. So this is at -1 now. And so let's, not too bad. So now this is the, well, all I've done is I've taken this and moved it 2 units to the left. So now this is the graph of y equaling log base 3 of x plus 2. Notice that, okay, that our x-intercept is here at -1, just like what we calculated. And the y-intercept is whatever it is. It's that too. Actually, I have it too high up, but it's wherever it said it was. It's not a very good sketch for that. And that's what the graph looks like. Okay. I guess that's it for section 4.3.